okay? So let's take a step back, okay, and say, recall, okay, the boundary value problem for v of x before, okay, what had homogeneous, okay, that just means 0, Dirichlet boundary conditions, right? So v prime prime plus lambda v equals 0, and then v0 equals v of l equals 0, okay? So what about something like mixed conditions, okay? And this is more like something you'll see on your homework, okay? So let's say that instead we had something like v prime prime plus lambda v equals 0. Left boundary conditions, pretty normal. Right boundary condition is this Robin boundary condition. Robin just means it involves the derivative and the function itself, right? Robin boundary condition. It's not a Dirichlet or a Neumann, okay? Let's solve this, okay? You're gonna solve it on your own. You could pause the video and do that, or you can just forge ahead and follow along with me, okay? Well, remember that this here, right? If you were to use something like the like a linear solution, right, for lambda equals 0, you would just get the trivial case there, okay? You can show on your own that transcendental, well, not specifically exponential type solutions don't work, okay? So it turns out in this case, the only thing that's going to work, right, is a trigonometric function again. And it's going to be the sine again, right? So remember that v0 equals 0 in this case. This thing is going to remain free, but the question of what the eigen value should be is going to be determined actually by my mixed, or sorry, my right boundary condition, my Robin boundary condition, okay? Now, it's not hard to come up with the equation, right? We just differentiate our function sine of x, right? Sine of square root of lambda x, and we get square root of lambda a cosine of square root of lambda l plus alpha a sine square root of lambda l, right, is equal to 0, okay? Now we can rearrange this, right? But inevitably, we're going to get an implicit function that we have to deal with. Lambda equals alpha tan of square root of lambda L, right? And so what's going on here? Well, the thing to do that you can do in this case, I mean, you can do this with software, or you can do this as just a sketch, right? Is to just start plotting your functions on the right and left side. So if I plot the function on the right side, right, that's a good old tan function. It'll look like this, right? And this occurs at, the asymptotes occur at pi over 2 L, right? 3 pi over 2L, so on, right? 5 pi over 2L, okay? And so if I then plot the left-hand side, right, that's just going to be a good old linear function that's going to cross here, it's going to cross here, and it's going to cross here, right? So I don't have a nice closed form solution, right? But I do have bounds, right, on my eigenvalues. I know that between n minus a half times pi and n pi over L, I'm going to get a one intersection, right? It's given by here because this is just pi over L right here. And this is 2 pi over L, right? And so essentially as n goes to infinity, right, this is going to get higher and higher. And then lambda n is going to approximately be pi n minus a half over L squared, okay? So aside from, numerical root finding using Newton's method, that's about all you can do. But you can certainly make a statement about the fact that as n goes to infinity, you'll continue to have these intersections, right? Because you always know that tan will continue to just repeat. It's a periodic function like this, and you'll keep getting these intersections with your linear function. So you do have an infinite set of eigenvalues, and that means you have an infinite set of eigenfunctions, okay? So n equals 1, 2, 3, so on, right? Okay. Now notice that was assuming that alpha was greater than 0. So without really stating it explicitly, right? I said here that, well, I'm going to take, alpha greater than 0 so that these things are flipped over. But what if I take alpha less than 0? Okay. If I take alpha less than 0, right, then square root of lambda is equal to absolute value of lambda tan square root of lambda L. Well, that's fine too, right? I mean, it's just going to look like this. Just going to flip the tan functions back over, right? And I'm going to have some function coming through here, right? It could cut through, it's going to cut through here, and then it's going to, again, start intersecting over and over again, okay? Now, this doesn't necessarily always work. Sometimes parameters like this, depending on whether you take them positive or negative, you may not get this repeat of intersections. And if you have a limited number of intersections, if you have a finite number of intersections, you have a finite number of eigenfunctions. And probably that means you don't have a complete orthonormal set. You don't have a complete set of eigenfunctions, and so you can't construct the eigenfunctions that you need to construct, okay? So you'll explore that a little bit in homework problem on your problem set. That's the book problem that you'll look at, okay? So that's sort of changing boundary conditions to change your eigenvalue problem a bit so that it's not so, it's not so trivial to work out the eigenvalues, okay? What about inhomogeneous boundary conditions, okay? What if instead of having some strange, Robin boundary condition, we just have inhomogeneous boundary conditions? They could be functions of time, okay? So let's go sort of all the way into a homogeneous problem where I'm also going to have forcing, right? I'll call that F now. Let's have X live on 0 to pi, okay, just so I don't have extra factors of L popping out. U of 0 is going to be a function I'll call U0, U of pi, I'll just call this U pi, t greater than 0, and then U of X, I already took up F, I'm going to call this phi, okay. So in this case, the steps are as follows, right? Start by solving the homogeneous version of the problem, right? So in actuality, right, you want to just solve this assuming that F is 0, assuming this is 0, assuming this is 0, and you can keep that free. So in that case, U of xt, right, is just going to be a separated solution. with some additional scaling coefficient here, okay? The second step then is to actually write out your inhomogeneity that's forcing you, your heat equation, itself as a Fourier series, okay, in your Fourier modes, okay? And so Fn of t now is going to be the integral from 0 to pi of f of xt sine of n x dx, okay? So that's how you get those time-dependent coefficients, okay? And the third step now is to note that even though u of 0 t equals u of pi t equals 0 in the homogeneous equation and in the homogeneous solution, okay, we can still obtain the right limits, okay? So the strange thing that's going to happen in this case is that the actual function values are going to be 0, okay? But the limit is going to essentially match with what you need it to, right? So this is your actual value, like this is u0 of t. And then this here is your limit as x goes to 0 from above. This is your limit as x goes to pi from below, but that's your actual value there, okay? So in order to do that, we're going to write Wn of t is equal to 2 over pi. I'm going to leave myself enough space there. Wn of t equals 2 over pi, the integral from 0 up to infinity, u of x t sine of n x dx, okay? So that means that Wn prime is going to equal 2 over pi integral from 0 to pi u sub t sine of nx dx. But what do we know? We know that that's equal to 2 over pi integral from 0 up to pi of uxx sine of nx dx. And then remember these time-dependent coefficients for f, right? So Wn prime of t is going to be equal to minus n squared Wn of t plus, right, something I'll call Fn of t, okay, where capital Fn of t is equal to my little fn of t plus these corrections now for the boundary terms that I would get from integration by parts, right? So essentially what did I do? I integrate this up by parts, right? But then this is gonna shed boundary terms that are gonna look like this, okay? So these are from integration by parts, okay? And so this, okay, along with the initial condition, Wn equals 2 over pi integral from 0 to infinity. Now we introduce our initial condition, right? Okay. So solving the IVP for Wn of t, okay, now gives the time-dependent coefficients, okay? And in this case, actually, the Bn term is just going to be 1, because that's taken care of by all these other restrictions that we have on Wn, okay? So what did we do? Well, we used the lessons from solving homogeneous equations to write down the Fourier series solution, but we didn't determine what these were yet. And then we said, well, how are we going to determine Wn of t? Well, we said there's a few things that we need to cook in now. First of all, we can introduce actually an inhomogeneity into the differential equation for Wn of t based on this forcing term, right? We can introduce an additional inhomogeneity based on the boundary terms that we would get by integrating this relationship by parts, okay? And then we have the initial conditions of Wn of t are just going to be given directly by the Fourier coefficients of phi of x, okay? So that works for inhomogeneous problems when you have forcing or inhomogeneous boundaries or both, okay? And if you want more details, they're also in the book, right? Sure. Okay. All right. So so that's it for the specific case of the heat equation. Okay.